Okay. Everyone sitting comfortably? Good. It's once again my great pleasure and honor to welcome all of you back here to our fourth and final keynote of HLAI 2016. In a way, we're actually now going to conclude the cycle of levels. So if you have you have to reorder them temporarily because you want more constraints, but if you have a look at Stephen Grossberg starting at the very low level modeling, then Gary Marcus making it a bit up the hierarchy. Now we will have John, and then there was David Aha, all up there on the very cognitive abstract level. So John is now going to conclude our little cycle through the different cognitive levels, if you want so. Who's John Laird? Most of you, I presume, or at least I don't actually know him. Nonetheless, let me quickly give you the basic bio facts. John is the John L. Tishman Professor of Engineering at the Artificial Intelligence Laboratory of the University of Michigan. When I yesterday introduced Gary Marcus, I actually said that he's one of the people who always make me jealous, because among others, he had a PhD with Steven Pinker's supervisor. You're second on that list, because you actually got your PhD with Alan Newell as supervisor. That was, I think, in 1983 at Carnegie Mellon. From 84 to 86, you have been as a research staff member at Xerox Palo Alto. And since 1986, you are faculty of the Computer Science and Engineering Division of the Electrical Engineering and Computer Science Department of the University of Michigan. You're probably best known for being the founder of Soares Technologies, which is an Argo company specializing in creating autonomous AI entities, and for your work relating to SOAR, which is the underlying cognitive architecture. And I think this is actually the longest list of fellowships we have over the 4 keynote speakers. So you collected all the A's, to the best of my knowledge. You're a fellow of HLAI, you're a fellow of ACM, and you're a fellow of HLAS. And on top of this, in order to also somehow distribute over the alphabet, you're additionally a fellow of the Cognitive Science Society. It's a great pleasure and honor to have you here. The stage is yours.
Thank you, Terry. So I want to thank the organizers for inviting me. It's a great honor to come and give a talk here. I feel like this is an audience that should resonate very much with the kind of research I'm trying to do. I'd also like to thank my funding agencies for supporting me, and I'd also like to observe that I am the John L. Tishman Professor of Engineering at the University of Michigan, and this is the John L. Tishman Hall for the New School. And so I'd also like to thank John L. Tishman, both for my engineering professorship and also for this hall. If you don't know who John L. Tishman is, he was in construction engineering, and he was responsible for the construction of both Epcot and the World Trade Center, and was known for his great work in construction engineering, and unfortunately he died last year. Anyway, for the beginning of my talk, I feel like I'm preaching to the choir. So you guys I get to be the preacher, you get to be the choir. So the way I want to start out is talk about the fragmentation in AI research. If you went to HLAI last week, how many talks did you see on general intelligence or biologically inspired cognitive architecture? Very few. What you did see were talks on this. Many different aspects of artificial intelligence. And the talks were mostly on one of those topics. And not on 2, not on 3, not how they fit together, but 1 or 2 of those topics. They also usually were on talks about tasks, individual tasks, like chess, question answering, maybe Go, furniture assembly, whatever. One of the interesting things about those systems is they could do that one task. AlphaGo is an amazing system. Watson is an amazing system. Deep Blue are an amazing system. But if you ask Deep Blue to play a game of tic-tac-toe, nothing would happen. So I think we see that there's not a lot of emphasis on generality. But there has been success, and there has been great success in the field of AI by concentrating on these, but I feel like they've done that, they've been able to do that because they have ignored a lot of the challenges that I think we in this room think about, which is the challenges of how all these capabilities fit together, how we build systems that work on many tasks, and how we have systems that work on many different tasks using different capabilities. So, my general view is the summation of AI technologies does not equal general intelligence. We have a lot more work to do. And my other view is that in terms of things like HLAI, where nobody's working on general artificial intelligence, we are not going to achieve general artificial intelligence by working on these components. It is not going to happen that we just put them all into a pot, stir them up, or connect them, or create a library, and general intelligence is going to arise. The only way we're going to get general intelligence is if we work on it. And I feel that this is the place where people are coming to work on it, and we need more people doing this. So this is the preaching to the choir, all right? The other observation is that in general, AI research is just not pursuing general intelligence. And I think we want to change that. Now, I feel like there is a way to think about how all these different components fit together that were on the previous page, not maybe all of them, but that is part of what I want to talk about in terms of how do we achieve general intelligence. So my research goals throughout my career have been to create general autonomous AI agents that use many different cognitive capabilities and pursue many different tasks. They also, we want to create agents that can expand those capabilities without programming. I don't want to resort to brain surgery to have my agents do new things and new capabilities. And that's the place we are now. Even learning systems. We have a human that sets it up as to what the task is. We encode what the task is in the system. We give it specific training instances in order to get it to learn. So it's just like, we don't have a homunculus in there, but it's like we have a homunculus on the outside, that these are very kept systems. So what we want to do is try and understand what are the research issues so that we can have autonomous AI agents that are able to use all these capabilities. And my own path has been very much inspired by human intelligence. And so let me take you on that path just a little bit. So this is what I consider a huge contribution from Alan Newell. It's just a table. But it puts a lot of things into perspective for me. This is orders of magnitudes of time, going from very fast speeds all the way up to months, approaching years. And each level is another order of magnitude. And it tries to organize what we think of the different levels of cognitive processing or underlying processing or rational processing or sociological processing into this kind of scale. So here's what's going on at the lowest level in terms of things on ion channels, neurons, neural circuits. This is the level of deliberative acts, compositional behavior, unit tasks, and so on. And I think one of the great observations is Newell wrote a paper that is scale counts in cognition, and that you have to look at this seriously. If you're building a neural net and you're going to say, well, I'm going to build a neural net that processes language by passing words down the neural net, and that's going to be sort of corresponding to, say, processing at a human level of about 1 second. I'd say there's a mismatch there as to what we know about, at least if you're going to try and do it the way humans do it. Neurons are down here, language processing is up here. Conversely, if you're trying to take a symbolic rule-based system and model what's going on in a neuron, you probably don't have your ideas very well organized. So what we want to do is think about how do we organize things this way. Now, there has been work in psychology that tries to organize this a little bit. People talk about system one. Kahneman talked about system one as being the low-level deliberative acts. You see a lot of interesting human behavior when you force people to behave quickly at this level. You can't force them to behave down at the 1 millisecond level. Nothing's going to happen when you ask people, okay, you've got 1 millisecond to do something. It's not going to happen. It's going to be the first levels here. And then the level above that is system 2, which is where you're combining things in the deliberative acts in order to get more rational cognitive behavior. And below that is what I call system 0. You can call it anything. But this is the level of implementation. For many people, this level is neural circuits. For me, I'm not worried about doing the neural circuits level. I'm going to do this with computer science. But I'm saying that there's a level right here, which is what we can build upon. And a lot of the behaviors we talk about are things that can get above that. So I'm going to focus in on this level right here, the cognitive level. Let's expand it. So here we have things that happen in about 100 milliseconds. Often we think about this as actually 50 milliseconds is a critical number. But from there we have compositional acts. This is where your mind is putting things together. It gets from different memories, things it's getting from perception. It's actually putting those things together. This is the indivisible acts below that. And then here are more complicated tasks you're doing. So here's reactive behavior, skilled behavior, primitive internal actions, accessing long-term memories. Here is where you're doing simple reasoning, such as doing mental imagery, doing simple language processing. Most of you can process language at the level of about 4 or 5 words per second. So that's, say we're doing sentence processing, it's about here. Above here is complex reasoning, analogy, planning, meta-reasoning, theory of mind. And my point is that when we look at AI, we should be conscious of these different levels. Are we doing work that's down here at this level, or are we doing work even that's below this, that's supporting the deliberative acts of the system? Are we doing work on simple reasoning or complex reasoning? If we are, then maybe we want to compare it to other works at that level. My hypothesis is there is a level down here we can start with, and we can build up from here, and that because what we see in human behavior is we don't see that when somebody's doing language, they're locked into processing language, and they can't do planning. They actually might do some planning while they're processing languages to figure out how they do attachments of prepositional phrases or whatever. And when they're doing planning, by the way, in the middle, they might interrupt themselves and say, oh, could you help me with this? So it's not like we have these modules at this level that's all that happens. Instead, what we see is what I call promiscuous intermixing of cognitive capabilities. Things at these levels up here are intermixing in real time among humans, and we don't have these as very strong limits between each other. The other thing we see is ubiquitous learning. We see learning is automatic and continuous, and it is not deliberate. One of the interesting things I think about machine learning is if I tell you I was born in Ann Arbor, Michigan, and you remember that, and I ask you tomorrow, according to machine learning, you didn't learn anything. That was just storing a fact. I hope that you being able to store those kinds of facts is a critical part of learning in humans. And I also think that one of the things is you can't control it. You can't stop yourself from learning, and you can't force yourself to learn. You can adopt strategies that help you learn, but you don't have control. So that is a level below here. And maybe, and just want to think about that in terms of learning. And one of the interesting things about human behavior is we're continually being able to compile reasoning and things up here down to this level down here. For example, when you learn to play the piano, how long does it take you to play each note the first time you do it? It takes you on the order of a second to 10 seconds as you look up and down, trying to figure out what note to play next. But through practice, you're able to compile that down into this lower level of deliberative acts. And that happens ubiquitously throughout human existence. So that's what I want to capture, is this kind of structure. And my hypothesis is that there are regularities at that 50 or 100 millisecond level that define a level of computation that we can build off of and do composition to get those higher levels. And that's the level we call the level of cognitive architecture. So that cognition, essentially complex mental behavior, arises from a fixed set of computational building blocks and the knowledge that you gain through experience. This is not my idea. This is many ideas, people's idea, but Alan Newell, back to my mentor, is the one I think who popularized it the best when he talked about how we could come up with unified theories of cognition as opposed to these fragmented theories of cognition. And that unified theory of cognition builds out of a cognitive architecture. All right, let me take a breath. Whew. All right, here we go. So let's continue on with this here, and let's look at some cognitive architectures and the kinds of timescales they attempt to cover. So here we have Libra, which is Randy O'Reilly from Colorado. That tries to model the neural structures and neural circuits and provide some compositional behavior. Spawn is by Chris Eliasmith and his colleagues at the University of Waterloo. You can model Spawn all the way down to ion channels, or you can take intermediate levels, but it tries to model more complex behavior, and they have a system built out of 1 million neurons that is able to perform 8 different tasks, and the tasks in real time take on the order of about 10 seconds or so. We also have models that are more psychologically oriented. They're trying to model the timescales of human behavior at the level of 50 milliseconds and above. EPIC was one that did human-computer interaction, whereas ACTAR has done almost all other aspects of behavior in terms of that. I would say ACTAR is sort of the 500-pound gorilla in terms of cognitive models for psychological modeling. There's also some that don't try to model human behavior explicitly, but try to get the functionality inspired by human behavior. And so Sigma is Paul Rosenblum's system, who will be giving a talk tomorrow. Companions is by Ken Forbes at Northwestern, and Soares is the system that I have. Now, some of these can be combined together. We haven't done that. In some ways, Sigma is significantly inspired by SOAR, but we've never, jointly put them together. But there has been work on putting some of these together. So Libra, if my animation works correctly, was united with ACTAR, and there's a system called SAL that sort of tries to span that whole thing. So that just gives you an idea. So what do we mean by cognitive architecture? So I'm going to talk about cognitive architecture in a few different ways. One, the structure of the cognitive architecture. Two, the kind of functions that they perform, and also the kind of memory representations they use. Now I put up here the standard model of cognitive architecture. This is together with Christian Lebert and Paul Rosenblum, we've tried to, and we're still trying to distill out, are there commonalities between many of these architectures? And we had a meeting 2 years ago where we brought people together, and there seemed to be a surprising consensus on what was some of the structures shared by many cognitive architectures. And the hope is that we can come up with a standard architecture that is not maybe right, and it's not maybe consistent with any one architecture, but what it does do is provide us a basis for comparing other architectures. It's a start of a conversation. If I want to talk to you about my architecture, I don't have to start from ground zero. I say, well, let's take the standard architecture and let's look at see how we differ on this component or that component. So let me talk a little bit about the structure. This is not that surprising. It's not like groundbreaking. It shouldn't be, because these things have been developed over the last 30 or 40 years. But we start with perception, getting information in from the task environment, and that processes information. Usually it's going to be statistical probabilistic processing. But in these models, it delivers a symbolic representation into short-term memory, possibly augmented with some numeric data. Short-term memory is the central place where all information resides that is describing the current situation for an agent implemented in one of the systems. So short-term memory, in order to access the long-term memories, information has to be in short-term memory. And from there, we can access declarative memory, which then provides us facts about the world, or potentially prior experiences of the agent, episodic memory. So sometimes there's a distinction between semantic and episodic memory. Procedural memory is what drives the system's behavior. Contents of procedural memory are matched against short-term memory, and through a process of action selection, a single unitary act is decided upon that can make changes to short-term memory, and those changes can either lead to more changes from procedural memory, can lead to the retrieval of information from declarative memory, or they can lead to action in the world. And this procedural memory, together with perception and action, leads to a cognitive cycle. Things come in from perception, procedural memory makes changes to short-term memory, and there's a cycle here until an action is selection and then action happens in the world. Associated with all the long-term memories are learning mechanisms. These learning mechanisms are all what we call online and incremental. They do not store things away and then do a huge amount of processing on the side. It's all adding knowledge as the system goes along. Each of the memories, the long-term memories, is mostly, has a combination of symbolic information, such as facts about the world, or often these procedural knowledge is done as rules, but they often have metadata, statistical metadata that is used in order to drive the retrieval. So for example, in ACT-R and also in SOAR, there is statistical metadata on the recency and frequency of how things were accessed in declarative memory. That's used to bias future retrievals so that you get things that have been important in the recent past. Some systems have metadata about short-term memory that is used as a forgetting mechanism, and similarly for rules in long-term memory. So we have a combination of symbolic domain knowledge as well as metadata to drive this. Now, I just showed here a single set of perception here, but clearly we have multiple modalities, multiple types of perception, multiple modalities for action, and so on. Now, if we want to really do general intelligence, we don't want to have a system that's just restricted to the kinds of tasks humans do well. There's a lot of tasks computers do well that we don't want to miss out. So I would say an extended model of this is we also want to think about being able to hook up with those other things that we're developing through other technology. So for example, we want to be able to have a way of interacting with software tools, but that will be through perception and action, not necessarily some other module up there. We might want to have a web search capability for the system. We might want to be able to use MATLAB. And instead of that being in the architecture, that would be something we access through perception and action. And finally, if I want my system to play Go, and I want it to play really, really well, it's unlikely that this kind of system is going to, it has better things to do in its life than just train itself on Go. So the best way for it to play a really good Go game is, how is that going to be? Let's have a separate module for AlphaGo on the side that it can call in order to find out how to play Go. I'm not saying that's the only way for it to play Go. I'm just saying we want to have an open mind about having these components. I now want to switch and be very selfish and talk about the architecture I've worked on through the years, which is called SOAR. SOAR was developed together with Alan Newell on the left, Paul Rosenblum. And if you're interested in SOAR, there's a book called The SOAR Cognitive Architecture that we published about 2012, 2013. It's available from MIT Press. So it's inspired by psychology and neuroscience. We look for psychology for cognitive mechanisms and capabilities. In one sense, SOAR is a cousin of ACT-R. It's consistent with many aspects of the standard model I talked about. But it was engineered using computer science. We look to computer science for efficient and robust implementations, and we worry a lot about making the system fast. Right now, on a laptop like this, it runs about 200 times what we would call cognitive real time. And that's with large knowledge bases and after hours of execution. It's available on all major platforms, including Windows, iOS, Linux, and Android. It does run on iPhones, and we have a little game in the iPhone store called the Michigan Liar's Dice, where you can play against SOAR. It's open source, freely downloadable, and it's integrated with many robotic platforms. It's in use at over 20 institutions worldwide, and hundreds of systems have been implemented in it. So here are some virtual environments we've done. Back in the 80s, we actually did a reimplementation of the expert system R1, but we've also done tactical aircraft, and this is the Liar's Dice. This is actually an art installation where SOAR watches someone using a Kinect sensor do dance, and it then interprets that and dances with it as this flaming creature. This was work done at Georgia Tech. We've also hooked up to a lot of robots. So I want to tell you about SOAR more, right? So we're going to talk about a simulated environment. We have an actual robot, but in order to talk about this, I'm going to just use a simple simulated environment. There's a robot, there's a bunch of packages, there's people, there's a stapler, that sort of thing. So this is SOAR as it exists today. So here we have the environment. We're going to just assume our sensor's giving us a little bit of information. Vision goes into what we call spatial visual system. This is the system's mental imagery component. This is symbolic working memory, which is really big, because I have to fill a lot of stuff in a minute. And it then has long-term procedural knowledge, long-term semantic memory, long-term episodic memory, and associated with each of these are learning components. So there's chunking, which is a rule learning mechanism, reinforcement learning, which does tuning of rules, and there's semantic learning, episodic learning, And then there's ways of doing action in the world, which include doing action in the semantic system and actually doing action in the world. So let's take it for a spin, okay? We're going to take it for a spin. So let's assume that we have some sensors and all we're doing is creating bounding boxes around our objects. And so here we get, in our system, we get a representation of Alice and the stapler that we can reason about in terms of the spatial situation and the relations. From that, we actually extract symbolic sensory data, and I've got to tell you, I'm showing a real abstract version of what happens in SOAR, just to be able to give you some idea of what's going on in the system. The sensory data comes in, and then procedural memory, which tests against symbolic working memory, might notice that it wants to, for some other reason, it wants to deliver a stapler to Alice. So it sees Alice, it sees the stapler, it selected the operator to deliver the stapler to Alice. Well, it turns out there's no way it knows how to do that immediately just in a single rule or in any other way. It has to decompose it into simpler parts. So it gets what we call an impasse in SOAR, which happens when it's not able to make progress directly. In the impasse, it might have a rule, such as the one at the top. If trying to deliver the stapler and the stapler is visible, then get the stapler. So then it selects the operator to get the stapler. It then has other rules that tell it to face it, so it then turns right to face it, and then watch for the very important animation down below. After it turns right, and then it turned right. So you see, it turned right, everything turned to the left. Anyway, it's the best I can do. All right? So we'll do that again. All right? Turned right, everything turned. Okay. So now it's turned right, it's now aligned with the stapler, and then it can have rules that say if you want to get the stapler, go forward, and then it goes forward and gets the stapler. However, things might not always work out the way we want them. What happens if the stapler isn't there? It's not visible. It's in another room. So in this case, the stapler's gone from vision, the stapler's gone from what's going inside, the stapler goes from there, and it goes out of input, the memory. So now it can't, the rule that was going to say turn towards the stapler doesn't fire, and now it gets an impasse, but it says it might have rules in the system, if the object's location is unknown, then attempt to retrieve it from long-term memory. All right, so then it will try to do a retrieval on the stapler position from long-term memory. It then does a retrieve to episodic memory and says, have I ever seen the stapler in a room? And let's assume that it hasn't. And so it tries to get that from episodic memory, it fails. So it says, well, that didn't work, so let's try to get it from semantic memory. What's the default room that somebody told me the stapler's always in? And so it then succeeds, and it gets it from the office. What I wanted to show you is that this mechanism of the procedural memory is what drives things. It goes and access these memories, use that to reason, and then drive behavior, and finally do action in the world. Sort of. It also can do reasoning in spatial memory. We haven't shown that here today. All right. So I want to summarize a little bit about the processing when we relate it back to Newell's level. So we have System 0, which is the architecture. That in SOAR is written in C code. And it retrieves knowledge from long-term memories in working memory. It does associative retrievals. It does automatic online learning. It's all the things that define the architecture. You never write C code. I never write C code. I don't even know how to write C code. I write SOAR code, okay? And SOAR is at the next level. I'm sorry, my graduate students write C code, okay? That's what they're for. No, they're indentured. They actually paid. System 1 is where we retrieve knowledge to select and apply operators. So that's the basic deliberative unit of the system. It can modify internal state, initiate retrieval, project hypothetical objects, initiate action in the world. And then System 2 is what arises from sequences of this. This is where we get complex reasoning. And I haven't shown you this, but this is where we get planning. This is where we would get analogy. This is where we get all the kinds of complex reasoning that take humans multiple seconds in order to do. So this supports compositional processing, combines knowledge across memories with inference and sequential decision making, and does planning and analogy. And also, as I said, the learning in SOAR actually converts this to rules that can work down here. So we've maintained that. Now, what I want to talk about next is if you saw what I presented with SOAR, one of the frustrating aspects was I still have to write rules in SOAR. There was a lot of knowledge encoded in the procedural memory. It happened that there just was the right rules that were there to do what we wanted. There was the right rules to get things out of semantic memory. There was the right rules in order to suggest operators in order to do a task. I don't think that's where we want to be. We want to be where we interact with our agents through natural means. When Amazon delivers me the robot in my dreams in 5 years, I don't want to have to open it up and program in Python or C. I don't want to have to call the kid down the street to open it up in Python or C. I don't want to have to call Amazon. I want to talk to it. I want to tell it what to do. I want to change its behavior through speech and language, and possibly demonstration. All right, so when we talk about interactive task learning, we want an agent that learns new task specifications. Using natural interaction, it comprehends the task description and uses its cognitive and physical capabilities to perform the task. It should not be dumb as bricks. It should be smart enough so that when I tell it what to do, it either does it because it has planning capabilities and other capabilities to do it, or it asks me an intelligent question. I also want it to learn fast. I don't want to teach it how to set the kitchen table by giving it 50,000 examples. I don't want it to learn how to vacuum by having it go around trying to do vacuuming 20,000 times. I want it to learn with me telling it once or twice, all right? I want it to be very fast. And I want it to learn, and this is just us being really geeky. We want it to learn so that it creates structures that are native to its architecture. In SOAR, that means we want it to learn rules that are similar to the rules a human is writing. We don't want it to learn some other representation that has to interpret and makes it run slow. We want it to run fast. So that's what we're all about. I'm not saying this is the only way we want to teach robots or agents like Siri, but it's one of the ways I think that we want to do it in the future. So in order for you to understand it, I'm going to show an example. This is a real-time example. This is James teaching Tower of Hanoi. We have a Connect, you can't see, system up in the upper left. We've got a robot arm, and we're going to play an isomorph of Tower of Hanoi because our robot can't pick up disks and put them on pegs. So we're going to have these 3 blocks that are going to define the 3-block Tower of Hanoi. All right? And so if you don't know what Tower of Hanoi is, then you're in for a treat because you're going to learn, I hope, along with the robot. If you don't, then I can't help you, okay? Now, one of the things I wanted you to notice is it's not just all strict the human teaching it. At one point, the human uses a term, a very obvious term, that the robot doesn't know, and so it asks for a definition. So there's interactive learning, and we do this a lot more on other tasks, but I just want you to notice it. So let's hope this works. We don't do live demonstrations.
The name of the game is Tower of Hanoi.
Okay, what are the actions involved in the game?
You can move a clear block onto a clear object that is larger than the block.
I don't know the concept clear.
If a block is not below an object, then it is clear.
So you just defined it for
Okay,
me.
I now understand the concept clear. I'm done with the action.
The goal is that a large block is on a right location, and a medium block is on the large block, and a small block is on the medium block.
I'm done with the goal.
So that's actually the goal situation, and it was useful for it to understand that in order to process the language. And now he's going to tell it that it's all finished instructing and it should go. It is now searching for a solution. It has now found a solution. So that is it using what it learned. What did it know before we started? It knew how to pick up a block. It knew what yellow blocks were, green blocks were, and so on. And it knew how to put down the block. It knew no aspects of Towers of Hanoi. All right. So, and this is, come on, hurry up. We're limited by the robot arm.
It was easy.
All right. It's the only laugh I get during my talks. Okay. So, here's processing we do in order to do task learning. We have perception of the environment. We then do language understanding in context. We construct an internal representation of the task, which is the goal, the actions, and other things. We then interpret that task representation in the context of the task in order to try to do it. We search for a solution to see if we can find a solution, and then we act in the world. Our emphasis here, in contrast to a lot of work, is on learning the task. A lot of people worry about, once you know the task, how do you do it well? We care about that, but we're starting with, how do you even know the task? Okay, so that's what we're trying to do here. So let's talk about perception of the environment. I told you that we have a Connect sensor. We're taking perception that's bringing in, we have little classifiers that we learn in terms of different colors. That then gives us labels because we were able to we take those categories. We then look those up in semantic memory because we've trained the system not on this example, but on other examples. We've trained it on what those colors are, and then it knows that that is a yellow block. So we extract all the relevant properties, and then we extract the mappings to words from semantic memory. So this is all using semantic memory, and here we have the internal representation. Now, it really would not say colored yellow. Well, it would say colored yellow because it would use the word yellow, but it also has all the relationships between objects and properties. And some of these things are things it learns how to compute through instruction. So the clear is not something it knows how to do until we teach it. So it gets a working memory representation. And just to show you that this is not a trivial process, I just want to show you that what does it really see when it's trying to move things around. What you see is if it picks up the block, suddenly the block disappears. And it completely disappears. And how does it know that when it puts down the block, it's the same block? A lot of AI systems cheat and assume the sensory system will somehow magically be able to keep track of what the correspondence is between the internal identifier of an object that it's manipulating and what's out in the outside world. In SOAR, we actually, with our spatial visual system, are hypothesizing where we think an object's going to go when the arm moves it. We look for it when it's there, and when we put it down, we hypothesize that that might be blocking or obscuring a block underneath, and so that other block underneath is still there. So this is stuff that a cognitive architecture lets you do, is put all these pieces together. All right. So the next thing we're going to do is parsing language. Language processing is all done within SOAR. Here's an example of an interaction that we just saw, actually. We have deliberative reasoning, which means a lot of knowledge in procedural memory and semantic memory is used to extract out the meaning of the word and then the meaning of a phrase and so on. We have a left to right, word at a time, repair-based construction grammar parser that we've implemented in SOAR. It generates a semantic structure of what that sentence means, and that's going to be used in the future. So just to give you an example of how we use context for disambiguation, if you see the sentence, move the red block behind the blue block, what do you think it means? And remember, you're a word at a time parser, which seems to be the way people go, and when you see the behind the blue block, you're thinking, I'm going to move the red block behind the blue block. But if this is what the situation looked like in the world, you would say, move the red block behind the blue block. Our system goes out and looks in the world and says, oh, is there a blue block? Oh, yeah, there is. Is there a red block behind it? Oh, yeah, there is. That's the red block I'm supposed to move. And then it goes along and sees to the right of the green block. And then it says, oh, that means over there. So it's using the context in order to help it do prepositional phrase attachment in this case. Here are just some of the sentences. I have to show them because I wrote the parser, and so I have to show off what I did. I actually did something. Okay, so we have, but this also is, the parser isn't the big deal here. It's the ability to define concepts using that language. So we're able to define new structures like clear or adjacent. We're also able to define things like if an object is on a boat, then there's a passenger of the boat. Anybody want to guess what task we're doing here? Come on, it's a toy task. Oh, very, well, no, it's the fox. It could be the fox, it could be missionaries and cannibals. All right. We could talk about losing. If more missionaries and cannibals are on a side of a river and the number of missionaries is greater than 0, then you have lost. So we can tell it this is a bad state. We also talk about legal actions, and we also can talk about complex things like in Othello. Now, I wished I could come up here and say, you know, you got this great, robust parser. You can walk up to the system and you can type anything you want. It's going to understand it as long as it sort of makes sense. No, I'm sorry, that's not the case. What we have is what we call a sufficient parser. You can write things that are sufficient to, it is sufficient to parse words and language that describe the task. But for now, it requires sort of an expert in order to specify. I just don't want to oversell this, okay? So we can do really great stuff with it, but it's not very robust. From all these structures that we create, we're able to then have everything put together, and then we do deliberate reasoning, and that creates a structure in working memory that's also stored in semantic memory that describes everything about the task we know. It describes the operators and so on. But that not means we can do the task, because we need to do the next phase, which is actually interpret and operationalize the task knowledge by taking what's in working memory, interpreting it within the current situation, and then figuring out that, oh, you know, given that my environment's represented like that, and I've got an operator called stack that takes 2 arguments, then I can propose an operator called stack that moves this object to that. So this is really where a lot of the magic happens, because we're taking this representation and matching against that. Now that's a very expensive operation to do, because we have to crawl down the structure, find everything, and match it against that. Luckily, in the background, we have chunking working, and chunking is building rules that do that whole process in a single rule, or a few number of rules. And what we see is that after we've done this, chunking, we don't have to do this deliberative process, and chunking gives us about an 80 times speed up. This system learns concept and relational recognition rules, operator proposal rules, goal tests, and the rules it learns are comparable to handwritten rules. After we've been able to decide to act in the world, the system tries to solve a problem. It does an iterative deepening search. If it can find a solution, well, sometimes it just knows what to do, but if it can't, it searches for a solution. If the search fails, we have a depth limit, it will go out and ask the human. The search can also fail because there's things unknown to it that it needs in order to do the task, and so it needs more help. And we'll see an example of that in a minute. Once again, chunking converts the search to rules that implement the policy so that we eliminate the search in the future. And in terms of the memory structures in SOAR, here's what we start with. So these are things we had to program by hand. I wish we didn't, but we did. Okay, so there's a lot of rules in procedural memory. There's a lot of structures in semantic memory, like the definition of different words. This is all the parsing. This is not to size. This should be a much larger block. But we have knowledge about how to interact with the human. We have knowledge about how to learn verbs and all that. This is all the kinds of knowledge we learn through experience and instruction. We learn action knowledge, how to do things. We learn knowledge that maps, that sort of knowledge I just talked about. We learn a lot of structures in semantic memory. We also are building up the agent's experiences. We can learn relations and spatial visual system, and we can learn perceptual features. So we've been able to teach it, I think it's like 22 games now, but at this time I created the slides. There's 17 games and puzzles. Some of these are isomorphs. So for example, this is the 8 puzzle. The way we play it is with a bunch of colored blocks, and you have to get the right color block on the right location. This is the famous frogs and toads puzzle. And this is how we solve the frogs and toads puzzle with blue and red blocks. Anyway, there's 17 games. It can learn all of them, and that's really cool. But what we can do is we can teach it one game after another. It's not a one-trick pony. It's a 17-trick pony, okay? So, what does that mean? What does this slide mean? Well, what we do is we take those 17 games, and then we run 3,000 permutations of them, all right? So sometimes tic-tac-toe is first, sometimes it's last, sometimes it's in the middle. When it's in the middle, there's varying different games that have happened before. What this shows is how many words did we need to teach the task. Why is it always the same number of words? Because if somebody has already defined 3 in a row, somebody's already defined clear for another game, we don't have to teach it when we get to tic-tac-toe. Thus, the worst case is when no game comes before us and it takes us this many words. As we teach it more games, the number of words we have to use gets less and less. So that's what we see with tic-tac-toe. What happens with all 70 games altogether? We see that many of these games have shared concept. Somebody in a talk this morning said, well, what does it mean to do transfer between games or tasks? This is one definition if you're teaching the task, is that can we transfer concepts? Now you can see that the frog and toad puzzle has very few concepts in common with any others. I believe it might have on, and that's taught in almost every game. So we get an improvement here. A lot of games, though, get significant improvement. So you do accumulate knowledge. It does help you in the future. We also get processing efficiency. As we do more tasks, we actually get faster on those tasks. There's a few tasks where we slow down on, and we don't really know why, but in general, the system speeds up as it learns new tasks. So now we've shown how to do this with games, but I showed all this stuff having to do with delivering things earlier, or picking up things for Sally. Let's look at how we do that as well with a mobile robot. Come on, baby.
Deliver the package to the Soares.
What is the goal?
The goal is that the package is in the Soares.
Please give me the package.
We don't have an arm on the
Okay.
How do I get to the SOAR
But
office?
notice it was able to ask, it was able to do one thing, but there was things it didn't know that it had to ask about. So it's able to partially solve the problem, but then ask for those parts it can't do. And once again, I remind you, that interaction is all real time. It doesn't sit there for 10 seconds. So here we're teaching deliver.
Okay. Please
And it
take the
never did the
package.
word deliver before we taught it.
Okay.
Now,
Deliver stapler to the copy.
different
Please give me the stapler.
different object, a different room. It's able to generalize from that one example and use, and we assume here that it does know where the copy room is and directly solve the problem. It is not learning solutions that are just one step after another that it has to perform. It actually learns a policy over the states that allow it to solve multiple problems. So, one of the things we did here is expand the system so that it could handle objects that weren't directly sensed. This is what the first thing we ran into when we went to the mobile domain. It turns out not everything is in the room that you need to pick up. So somebody might say, fetch the stapler from Sue. Well, what if the stapler isn't here or Sue is not here? As you saw in my earlier example, there's ways of getting information about this from its long-term memories. We didn't want to program that in. So we added instructions to the system, such as think about the last place you saw the stapler. That would lead it to use episodic knowledge. Recall the usual office for Sue. That would lead it to use semantic memory. And not only would it use it for this task, but it would learn that these are things it can do in the future when it's trying to solve other problems, so that as it ran into problems where it had a person it had to find, it would look them up and not ask that question. When all else fails, it will say, I don't know, and the human can say, I don't know, and the system will go off and explore and try and find it. So let me summarize. I think cognitive architecture is a great framework for creating general artificial intelligence. I think it's there might be many, but I think it's a real serious contender for a path for us to pursue to reach general artificial intelligence. I think SOAR is a prime example of it. It has many of the capabilities. It's scalable. We have a lot of experience with it working on many tasks. I think interactive task learning is a real great challenge problem for AGI, BICA, and for HLAI. I think that this kind of problem of how do you take an external specification and internalize it and do a task is a great problem for many of us to work on. We're scratching the surface on it right now, but I think it really changes the way we think about AI systems, because instead of us having to program them, they're going to have to take in an external specification and do it themselves. There's still much to be done, especially in interactive task learning and in AI cognitive architectures in general. We want to make these systems more knowledgeable. Right now, we don't start with a huge memory. We have loaded in WordNet in the system and done some experiments with it, but we need to be able to get access to large external knowledge sources so the system doesn't ask stupid questions. It can get them on its own. We need them to be more autonomous, better in interaction with their environment in terms of perception and action, more self-motivation, more agent-driven learning and discovery. Research here that people have talked about is directly relevant to this. We also need them to be more social, better language skills, better dialogue, modeling each other, being able to interact with humans better. So I think there's a lot to be done in terms of cognitive architecture. There's still a lot to be done with human level interactive task learning. Let me stop there and see if we got any questions. All right. I guess the standard thing is if you have a question, you come on down. Is that right? Yeah. And I can use this microphone now. Go ahead.
I would like to ask how many things did you have to code into the system? So you didn't pretend that it knew everything by itself. So you did say that you coded some things. But for instance, I was wondering, did the robot told said to the person, give you the package. So if someone knew that the person had the package, how did it know that, for instance?
Right, so we are faking sensing a lot here. So it does not have very good sensing. So so the system starts off with, in that case, primitive actions about how to move around and how to ask for things and how to give and ask for objects and then how to give objects to people. In that case, it assumed that, I believe we had pre-programmed in that that box was in that location. Definitely one of the things we want to do is be able to have the system sense its environment and make that determination on its own. But that's engineering on the vision side that we haven't gotten to yet. Yes?
So the background is the question, when do we get human level AI? But the specific question is, how long before it can learn from instructional text written by people who aren't expert in a very specific
So 5 years ago, I would have said human AI is a long, long time away. And the reason why is that not many people are working on it. In fact, a quote from Herb Simon back in the 60s, when asked why were there predictions about how fast AI was going to come along, general AI was, he said, well, we really misestimated because people stayed away and they stayed away in droves. So I think a lot depends on how much research people put into these things. Right now, this kind of parsing where you go from words to semantics that are grounded in the world is not done by the majority of this language community. They're still looking at how to do statistical-based parsing that doesn't really give you semantic representations, but gives you, some intermediate representation. So I think the answer, you can't answer the question until you know how many people are going to be working on this. In terms of me and my students, the next big research problem is not necessarily to make this so that any human can walk up to it and do that. That's a huge research problem in language. It's something we will be working on in the background, but I have no way, I'm sorry, I just can't make predictions like that. It's impossible to know. Language is really, really hard. So I don't think that we're just scratching the surface of it. And I think part of it is that we have to get to systems that learn about language by reading themselves. By them reading, not reading, but reading. And I think we're still a ways from doing that. There are efforts out there to do that. Early efforts like Tom Mitchell's work on never-ending learning did not end well. They ended up trying to mine the net for the World Wide Web for lots of information, and what they found is lots of junk. So I think this is a real challenge coming forward. Sorry. The question from Turkey.
Hello.
Hello.
Well, so I'm not speaking in the name of all Turkish.
Okay.
Thanks for the presentation. You mentioned the future goal, which was learning from few examples.
Well, no, that's what we can do right now.
Okay, so
We actually learned, everything you saw, it was learning from those single examples.
okay, so all right. So how can you achieve learning from as few examples as possible? Is the question.
So you have to, the couple questions that are critical is what's the representation you're learning and what are the characteristics of the environment. So one of the characteristics of games is they have deterministic rules. Or not deterministic rules, I'm sorry. They have specific rules. They have definitive rules. So the rules don't change. Every time you play the game, it's not like you're trying to find the middle of a Gaussian to figure out what the rules are. We don't give it, oh, here's something that's close to the rule for tic-tac-toe. Here's something that's close to it. We tell it exactly the rule. So if it's able to know that it's getting exactly the right information, it can analyze it a lot in order to derive what the general characteristics are. So that's one of the ways this is different than trying to learn to recognize cats. Okay? And I think that a lot of human learning is like this. A lot of early human learning is like learning to see cats and learning to control motor mapping and stuff like that. But there's a lot of human learning that we can learn very fast. And so I think that's the thing we're emphasizing here.
Two questions. One, is it possible to learn spatial primitives? And second question related.
Let's do one and then follow.
Okay.
So we have spatial primitives that have to do with alignment across axes like X and Y and Z and things like distance. And we can learn spatial predicates such as to the left of, to the right of, above, beyond, behind, and also near, based on statistical regularities and how near and some is used. From there, we build up more complex spatial compositional structures such as adjacent or things like in Othello, things are between each other. So it starts with very much primitives. I do not believe we have the sufficient primitives to learn all the kinds of spatial things you want to do. And there's other research in spatial learning that is more advanced than what we do. We sort of did, once again, what was sufficient to bootstrap us up into these games and things like that. I think more work could be done there. Let's take question number 2.
So when you learn spatial predicates based on existing spatial primitives, is it done just through instruction? Is it done in the following way, like behind means something versus block A is behind block B?
So I think you're asking what is the coordinate system we're in, and we're in a.
No, not the coordinates. Is how the learning happens. Like
So usually the way it happens. So for example, for properties like red or something, the person will use red in say pick up the red block. The system says, I don't know what red is. And then we will say, red is a color, and it does know that there's 3 properties it cares about. So this is baked into the system: size, shape, and color. And then it will ask for an example of red things, and you can point to them or say, use other language to indicate that. For spatial relations, it will refer to objects in the world that it is able to ground its language to. And you can say, the red block is to the right of the blue block. And then it tries to look for what is the simplest explanation for that given the spatial structure. And I now turn to James, who implemented this. Is that pretty correct?
Yeah.
All right.
Thank you.
I've listened to enough of his talks. Okay. Yes.
When there are choices, like in the Tower of Hanoi, move a blue block to 1 or 2 places, how does it resolve the choices?
Right. So in all of these puzzles, the reason there's puzzles is there's choices. And what it does is a look-ahead search where it uses a model of what it knows it can do with its actions. So it says, oh, well, I can pick up this block and put this one here, given the constraints that were told me about this game. So, for example, in Tower of Hanoi, you can pick up a block and you can put it on a location or on another block that's larger to it. So it has internalized that knowledge, and it only proposes those, what we call operators, that are consistent with those constraints. And it also then knows, based on its underlying model of doing action in the world, what will happen when it does that. So it does a look-ahead search. It's called iterative deepening, where it looks depth 1, depth 2, depth 3, depth 4. And it looked all the way to the end, actually, for Towers of Hanoi, which I think is about 8 deep or something like that. It's 7? 7 deep in this case, in order to solve that problem.
So to pick the shortest one, or some other evaluation?
It will, because it's an iterative deepening search, it will give it the shortest solution. In that case, we use iterative deepening when the little robot's rolling around and it has to plan between different rooms. We actually have pre-encoded in an iterative A-star algorithm, so it does do an A-star search internal to do that. Hi.
You started to talk about the coordinate system. I was just curious of how it deals with the egocentric or global world.
Yeah. So I'm going to expand on the question. The question is which coordinate system it uses, and can it change coordinate system based on what the human says? Is that the right question?
Exactly.
No. Right now we have one coordinate system which is egocentric. Well, yeah, it's sort of egocentric, although it's sort of centric to it depends sort of on the observer. It's sort of, I guess, observer-centric. So when we say left of, but it maps it onto things internally. But we don't have a way of saying, think about it from your perspective, or, you know, somebody's coming in stage right. We don't have those capabilities. I don't think it would be that difficult to add them to the system, but that's not where we are today. I mean, a lot of this is, these are great questions, and we love to do all this. I mean, part of this is opportunity costs. We're trying to do those aspects that are sort of pushing the state of the art as much as possible.
So are landmarks considered part of the episodic memory?
Landmarks are in semantic memory, but they are stored in episodic memory. So I'm sorry, when it learned where the SOAR office was, that was stored into semantic memory. So in the future, if you ever said, go to the SOAR office, you could look it up. But episodic memory is just saving that away as well. So we see episodic memory as being very useful for cases where you don't know that it's useful to store something into semantic memory. So if you just happen to go into a room and you see a blue object or a stapler or whatever, you might not think, the system might not automatically store that into its semantic memory, but it can always go and ask episodic memory, when was the last time I saw a stapler? All right, well, thank you very much, and if you have other questions, please feel free to email me or see me after the talk.